Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
So, up to now, you learned the main steps of the membrane selection process, such as the membrane separation size, membrane materials, and membrane modules. Let's look at the last step, decision of the process. In this step, you can learn that how to determine the operating mode and some basic principles of the pressure vessel configuration and skids. Operating modes. Like the choice of the module, the operating mode of a membrane process is determined by the load or the concentration of the dissolved or undissolved constituents of the respective wastewater or process water. The specific energy demand of the operating mode influences the economic efficiency and with this, the feasibility of the individual applications. As a rule, membrane processes are operated in cross-flow mode, also called tangential flow. In cross-flow mode, the feed is pumped parallel to the membrane surface and the permeate is withdrawn diagonally to it. When sufficient pressure or concentration differential exists on the surface of the membrane, modules smaller than the surface pores will be driven through it. As I have already discussed, this solution that passes through the membrane is called permeate, while the solution rejected by the membrane is called the concentrate or retentate. As I have already mentioned, this solution that passes through the membrane is called the permeate, while the solution rejected by the membrane is called the concentrate or retentate. Tangential flow to the brine or concentrate side of the membrane attempts to limit the development of a covering layer on the membrane and to maintain a constant permeate flow at the highest possible level. Cross-flow operation is used in nanofiltration and reverse osmosis. In ultra and microfiltration, both operating modes are possible. The dead-end operation stands in contrast to the cross-flow mode. In dead-end operation, a covering layer develops on the feed side due to the retention of suspended material which decreases the filtration capacity. As a result, the permeate flow decreases during the process. Combined with an effective backwashing technique, this operating mode is used successfully in microfiltration and ultrafiltration applications. As you can see in these graphs, filtration intervals in dead-end operation have shown the decrease of the permeate flow at the constant feed pressure at the target top and the increase of the feed pressure at a constant permeate flow at the target bottom over the filtration interval. By removal of the covering layer during the backwashing interval, ideally the original filtration capacity will be reached again. The combination of both operating modes is called semi-crossflow mode. Both operating modes, dead-end and crossflow, differ considerably in their energy demand. Pure cross-flow processes need between 2 to 10 kWh per cubic meter for microfiltration and ultrafiltration, or between 0.5 to 5 kWh per cubic meter for nanofiltration and reverse osmosis, while pure dead-end processes operate only with an energy consumption of between 0.1 to 0.3 kilowatt hours per cubic meter. Pressure vessel configuration and skids. Pressure vessel modules are generally 100 to 300 millimeters in diameter, zero point 0.9 to 5.5 meters long, and arranged in skids, also known as rocks, banks, or units in some design manuals and regulations. Typical pressure vessel membrane elements are shown in the left figure. A single module typically contains between 40 to 80 square meter of the filter area. Skids contain between 2 and 100 modules depending on the capacity requirements. Skids and modules in a full-scale production membrane filtration system are shown in the right figure. The skid is the basic production unit and all modules within one skid are operated in parallel simultaneously and can be isolated as a group for testing, cleaning, and repair. Each module must be piped individually for feed and permeate water, so large skids involve a substantial number of piping connections. Feed pumps typically deliver water to a common manifold that supplies each skid. The feed pump increases the feed water pressure while the permeate stays at near atmospheric pressure. Pressure vessel systems typically operate at transmembrane pressure between about zero point 0.4 and 1 bar. As I said, transmembrane pressure is a pressure drop between the feed and permeate side. Pressure vessels also can be configured with either outside-in or inside-out membranes. Now we finish the steps for selection of a membrane process. Let's have a summary of the characteristics of the microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Characteristic features of microfiltration and ultrafiltration. As you can see in this table, there is a list of membrane characteristics that we have already discussed, such as operation mode, operating pressure, separating mechanism that we will discuss about the separating mechanism in the next sections. Molecular separation size, material and structure, and module types. As you can see, microfiltration and ultrafiltration operate in both cross-flow and dead-end mode. The operation pressure for microfiltration is less than 2 bar, but ultrafiltration can operate less than 8 bar. The separation mechanism for both is screening with a difference in separation size. The solids larger than 0.1 micrometer can be removed using microfiltration, and the solids larger than 0.01 micrometer can be removed using ultrafiltration. While the symmetric structure is predominant for the microfiltration, the asymmetric structure is more common for ultrafiltration with polymer or ceramic materials. Spirel-wound, Hallow-fiber, tube modules, and pellet modules can be applied for both. Characteristic features of nanofiltration and reverse osmosis. Nanofiltration and reverse osmosis can operate only in cross-flow mode to reduce the membrane problems. Material and structure and module type for both membranes are generally similar. The separation mechanism for both is solution diffusion with a difference in separation size, as the dissolved solids bigger than 200 Dalton can be removed using nanofiltration, and dissolved solids smaller than 200 Dalton can be removed using reverse osmosis. Another difference is in operation pressure, in which nanofiltration can operate up to 40 bar, but reverse osmosis can operate more than 70 bar and sometimes in special cases up to 120 bar. Now the first section has finished, and in this section you learned how to select a membrane based on the molecular separation size, material and structure, module type, operating mode, and etc. We continue with section 2, and you will learn in this section about the membrane problems such as fouling, scaling, and concentration polarization, and how to minimize them. Thank you so much for your attention.